And I sort of tried to ask the following two questions. Number one, how machine learning can impact scientific computing and computational science. And number two, how numerical analysis can impact machine learning. So how can we help machine learning with the viewpoint of numerical analysis? Typically, when people look at machine learning, it's theoretical computer science viewpoint or statistics viewpoint, or sometimes information theory viewpoint. But I like to say that actually numerical analysis is very, very helpful in terms of understanding machine learning or build better machine learning models. So let me start with a summary of what machine learning can do. And I say machine learning can do wonders. So here are some examples of the kind of things machine learning can do. So the first example is this very typical example in artificial intelligence. Namely, you're given some data set consists of these images, and these images contains are classified into birds, dogs, deers, and according to what they have on the image. And you're supposed to learn a function which tells you what the image is about. So this is the function that defined on a space of images. So the function f star maps each image to its category. So here we have 10 categories. So this is a discrete value function with 10 values. But each image is a point in a 32 by 32 by 3 dimensional space. 32 by 32 because that's the number of pixels, and 3, that's the dimensionality of the color space. So what we're doing is try to approximate a function from 3072 dimensional space, defined on 3072 dimensional space. So this is a function approximation in very high dimension. The second example is this. So what you're seeing is a bunch of human pictures, pictures of human face. All these pictures share one thing in common, namely they're all fake. They're not real human faces. So what's happening here? Well, you can think of pictures of human faces as a random variable defined on the space of images. And then for that random variable, we don't know the probability distribution of that random variable, but we do know a finite number of samples, namely pictures of real human faces. So from that finite sample, one can actually learn the underlying probability distribution accurately enough and sample new points, produce new samples. And these new samples are these fake images, fake human faces. So this is learning very high dimensional probability distribution. A third example is very well known. This is the Alphago. We all know Alphago was able to beat humans. But what we also know is that the optimal strategy for the Go game, given the strategy of the opponent, obeys some Bellman-like equation. So Approximation was really trying to solve a Bellman-like equation in a huge space. And you can solve that equation sufficiently well so that you can produce a strategy that beats all humans. So all these examples about doing solving some mathematical questions in very high dimensions, so approximating high dimensional functions, approximating high dimensional probability distributions, solving high dimensional Bellman-like equations. So these are all, so how can we do this? Well, these are made possible because now we can accurately approximate high dimensional functions using a finite piece of data. Now, associated with the high dimension problems, there was a very common, very well-known problem, namely the curse of dimensionality. So all these issues that we couldn't deal with before because of the curse of dimensionality, which means that as dimensionality grows, the computational cost grows exponentially fast. That was the problem. So because of the success in solving the kind of problems that I just discussed, maybe this opens up new possibilities for attacking other problems that suffered from curse of dimensionality. So this was the thing, this was the idea that we were thinking about several years ago, and we tried them on several examples. Let me give you some examples. The first example is a protein folding. So this is a very small protein, trip cage. It's got 20 amino acids. So I want to solve this protein folding problem using multigrid. Well, first of all, what is a protein folding problem? We have an energy function which depends on the positions of all the atoms in this protein. So that's a very high dimensional function, which is supposed to be given, that describes the interaction between the atoms, chemical bonding, van der Waals interaction, electrostatic interaction. So we're supposed to minimize this function. Well, in reality, we don't minimize the function. We actually sample a probability distribution. But let's think about it. Let's just think about minimizing this function. And as I said, we want to solve this using multigrid. So how do we do, what is the usual multigrid? We usual multigrid, we solve this quadratic minimization problem, where usually LH is in the discretization of some elliptic operator. And UH is, say, the solution of a finite element discretization on some fine grid. Well, in multigrid, we have a projection operator that maps to functions on coarse grid, and then we have an effective operator on coarse scale. And that effective operator is very easily defined through this projection operator. And then we just minimize the similar function on the coarse grid, and then we iterate. That's multigrid. And suppose we want to do a solve using this idea for a nonlinear problem. Well, we started with some nonlinear minimization problem, and we can define some projection operator or coarse grading operator. And then the next question would be, how do we define the effective effective operator or effective problem, optimization problem on the coarse grid? We don't know. And that difficulty was essentially the main obstacle in applying multigrid to a much larger class of problems. So now, well, now we can say, well, let's approximate this function by the difficulty is that this is a very high dimensional function that we don't know. So now we have the option of approximating this high dimensional function using some neural network model. Never mind how to actually do that, but in principle, we could do that. And once we've done that, then we can implement multigrid in the usual way. And that is done for this, that's how this thing worked out. So we started with the extended version or extended state of the protein, and we did some, develop some algorithms to perform what I just said, to do this. Okay, now one thing about, one thing about approximating these high dimensional functions is that we need data, we need to collect data. So that's an issue that needs to be dealt with. And then this collecting, the collecting data means that you have to solve some fine scale problems, produce some configurations, and that's expensive. So typically in these applications, we need to do some adaptive sampling. Namely, we want to produce on the fly the best data set, and that's an issue. That's an issue we have to address. Well, we developed an algorithm to address this that has some similarity with fine element because it's an adaptive strategy. The idea is that you kind of explore the configuration space. For example, here we want to look for a function of this coarse grain variable. So we started exploring this configuration space of the coarse grain variable using some Monte Carlo algorithm. And each state, we need to produce some microscopic state that's consistent with this the coarse grain variable. And then we need to decide whether this state needs to be whether we need to collect data on that state. So that's done by some sort of a priori error estimates, a posteriori error estimate, much the same way as in finite element. Now the details of that shouldn't matter here because it's not, there are many different ways to do this, but doing so through this kind of a strategy, one can develop an active strategy that produce data on the fly and then train neural network models at the same time. And this is very important, as I'll show later. Okay, so that's one example. I know I didn't give you the details, but I hope I give you some sort of feeling of how these problems can be tackled now with the help of deep learning. Second example, I'll go through this quickly, is the molecular dynamics. Molecular dynamics is a very fundamental tool in chemistry and material science. It's just solving Newton's equation for the nuclei of all the atoms in the material or in a molecule. Well, in order to do that, we need to know the potential function of that system, which describes how the nuclei interact with each other. Classically, there are two ways to do this. One is just guess, so empirical potential. That's just try to guess a formula with some coefficients, and you fit the coefficient with some data. And that's how things work in classically in molecular dynamics. For example, you might know Lennard-Jones potential, EM potential, Stigler-Weber potential. These are all examples of these empirical potentials. The other way to do it, developed by Kahn Perinello, is to calculate this force, atomic force, on the fly, using some quantum mechanics model. For example, density functional theory. So that's another way to do it. And these are called ab initio molecular dynamics. Now, in these two strategies, one is very accurate, but not very efficient. Kahn-Perinello molecular dynamics can handle 1,000 atoms, and that's about it. And empirical potential is very efficient, of course. You can do millions of atoms, but it's not reliable. So the new idea would be the following: that we use quantum mechanics model just to supply the data, so we can calculate quantum mechanics models for small systems and collect lots of those, and then we use machine learning to train a model for this function, approximation for this function V, and then we just do classical molecular dynamics. Of course, to do that, to do this really reliably, there's lots of technical issues that one has to deal with, but this can work out very well. So these are some results of comparing machine learning produced in the machine learning model prediction and the results of EFT, the quantum mechanics model, across a very wide range of different systems, from small molecules. This is aspirin, this is ethanol, and this is big molecules, pyridine, and these are high entropy alloys, surface materials, simple metals, stuff like that. So you can see it's almost uniformly accurate for a very large class of systems. Now, in order to do this, so here I want to emphasize that what we want to do is we want to produce a model that we can rely on, that we can trust, just like the quantum mechanics model, just like the Schrödinger equation. We want to produce a model that's very reliable. So in order to do that, you have to make sure that you have the right data set, as I just emphasized before. And this, let me show you the importance of generating the right data set. So here, let's look at this example. We want to produce a reliable model for simple alloy. And we started, and you do this, which means you have to have a data set that's representative enough of all the configurations that you might see in practice at different temperature, different pressure, solids, liquids, and stuff like that. At the same time, each label, the data set, is a quantum mechanics calculation. So that's very expensive. So you don't want to do that many times. So you want to sort of produce the minimum data set that's representative enough. So small data set, but not smaller. And you see this in this particular example, the exploration scheme explored 500,000 configurations, out of which only less than 20,000 were selected to be labeled. So meaning calculate quantum mechanics force and energies. So that's, if we had to label all these configurations, we would never be able to finish. So that's very important. And this is one theme that can constantly occur in our machine learning problems that doesn't show up in machine learning problems in the computer vision. For example, if you go back to the first, to these problems here, these data are labeled beforehand. So in computer science, there are two groups of people. So one group of people produce the data. The other group of people do the machine learning. And we don't have that luxury. We have to do this at the same time. So that's the one point I was trying to make. And you can see this kind of what is called non-DeepMD has become a very powerful tool. Perhaps the most powerful tool now for ab initio molecular dynamics. So this is the example of implementing what is DeepMD on the Summit. This is the second fastest computer on Earth. And you can see that one can now handle simple systems like copper with hundreds of millions of atoms, 5 orders of magnitude improvement. For water, so relatively complex system, you can do millions of molecules. So these are very dramatic improvement. And this is an example of stochastic control. So I mentioned this is because it's the first application of deep learning to scientific computing. So stochastic control is, we have a discrete dynamical system. This is the noise, and S is the state, A is the control. And we want to choose the control to minimize this objective function. So we have the running cost, we have the terminal cost. And here we're looking for some feedback control. And again, we parameterize this control by some neural network, never mind how we actually do that. And then the problem becomes choosing these network parameters to optimize this function. So this thing has a lot to, this looks exactly the same as this, except now we are minimizing over the network parameters. And if we draw the network structure, so we go back. So if the horizon is T, big T, then we have, in this formulation, we have T networks. So we have T networks. Each network has its own parameter. And then we optimize these parameters by we choose these parameters by optimizing this total cost here, which is sum through all these networks. So this is a composite neural network structure. We have, these are sub networks for each, for the feedback control at each time step. And these can also be solved and works out very well. So this is a meta problem of energy storage with multiple devices. N is the number of devices. As you can see that as iteration goes on, the convergence is quite nice, and these results can be calibrated with other methods. My last example is solving nonlinear parabolic PDE. So this is a nonlinear parabolic PDE. I formulated as a terminal time problem. So this has a wrong sign, but because of the terminal value problem. That's because in order to develop an algorithm to solve this class of PDEs, we want to reformulate this PDE problem in terms of a stochastic control problem, very much like what we had before. In order to do that, we make use of the tool, so-called backward stochastic differential equations developed by Etienne Patou and Shigo Peng. And they proved, well, they didn't prove in their paper, but there's a subsequent paper which proved that, what is called nonlinear Feynman-Katz formula, that this problem is equivalent to this problem. Namely, we minimize, we define these forward and backward stochastic differential equations involving the processes x, y, and z. You can see that there are two equations, 3 unknowns. So what's remarkable is that it's proven in this paper that it has a unique solution, it has a unique adapted solution. That's quite remarkable. And we minimize the discrepancy between the terminal condition and the value of the process y at the terminal time. So one can show that these two problems are equivalent. And once formulated this way, it's very much like the stochastic control problem. we minimize something subject to a dynamical system. The dynamical system is like the constraint here. So the same kind of algorithms can be applied to this framework, and you can, I'm going to skip the details. You can see, as an example, let's consider this so-called linear quadratic Gaussian problem, which is a canonical problem in stochastic control, and this is our cost function. The Hamilton-Jacobi-Bellman equation is this Hamilton-Jacobi-Bellman equation. And for this, it's well known that we can apply the Hopf-Kohl transformation, and then we can write down the exact solution. This is the exact solution. So that can be used to calibrate the numerical algorithm that's described here, which is very much like the stochastic control algorithm. And you can see the results agrees quite well. Okay, so another example, this is actually how this algorithm is applied. It's becoming quite popular in Wall Street, where people use this algorithm to calibrate exotic options. This is Black-Scholes equation, but nonlinear Black-Scholes equation, because some nonlinearity, this is a cubic nonlinearity that represents some default risk is included. So one can solve these equations in hundreds of dimensions and get good accuracy. Okay, so these are kinds of things that we could not have imagined that we could do. Maybe 5 years ago, we could not have imagined we can do these kind of things. Now, a very natural question is why? How come that we can do this? There's the two big mysteries are, first of all, why do things work in such high dimension? So how can we do this? And secondly, well, we all know that neural networks requires extensive parameter tuning. You have to be very good at tuning parameters. So why is that so? So why is it so sensitive to the parameters, how the so-called hyperparameters in the neural network model? So but there are other questions. So there are lots of mysteries about in neural network models. And secondly, the fact that the performance depends so sensitively on the parameters suggests that they're almost like ill-posed problems. Ill-posed, it's not like we cannot solve any of those. I mean, if you tune it very, with a good initial condition, if you tune it very hard, you may be able to solve, produce some reasonable solution to an ill-posed problem, but it's just not stable at all. Well, machine learning is not that bad, but it has that flavor. So can we formulate better machine learning models that are more robust? Okay, so these are the questions that I'll try to address. Of course, there are lots of things that we don't understand, but let me try to just address these issues. Well, let's start with approximation functions. After all, what's really going on is now we can approximate very high dimensional functions, some classes of very high dimensional functions. Well, first of all, let's go in the classical setting. We try to approximate functions by polynomials or piecewise polynomials. There's a universal approximation theorem, the Weierstrass theorem, which tells us continuous functions can be approximated by polynomials on compact sets uniformly. And then Taylor's theorem tells us that convergence rate of this approximation depends on the regularity of the target function, how many derivatives there are. In particular, in classical approximation theory, we have these kinds of theorems. Namely, this is not a precise statement, but this precise statement is very close to what I'm going to say. A function can be approximated by piecewise polynomials if and only if that function belongs to some Sobolev or Bessel space. Okay, sorry, let me do it over. A function f can be approximated by piecewise polynomials with the specified rate of convergence alpha, if and only if that target function belongs to some Sobolev or Bessel space. Okay, now notice that the results like that suffers from cursive dimensionality because the mesh size h here, by the way, the h is the size of the mesh. When you do the piecewise polynomial, you have to have a mesh. H is the size of a mesh. And M is the number of total parameters. So H is related to M by this. And D is the dimensionality of the problem. So this 1 over D in the exponent says that if you want the error to be less than epsilon, the number of parameters needed roughly scales like epsilon to the minus D. So epsilon, if alpha is equal to 1, for example. So if epsilon is 0.1, this is 10 to the D. And 10 to the D when D is equal to 3000 is a huge number. So this is the why classical piecewise polynomials, finite elements, finite difference, wavelets, all that stuff don't work in high dimension. Now, there's one thing that we do very well in high dimension. That's statistical physics. People in statistical physics calculate very high dimensional integrals, millions of dimensions routinely. So how could they do that? Well, they do that by Monte Carlo. Suppose we want to calculate this expectation, and then you do this, you pick xj to be IID samples of the probability distribution mu, and then you do this, you approximate this integral by this sum. The error, this is exact, the error is given by the variance of G over M. So there's no 1 over D here. So the convergence rate is independent of dimensionality. Of course, this coefficient could be large, could be very large. So that's why in Monte Carlo method, we talk a lot about variance reduction, so different variance reduction schemes. Well, what we want to do is something similar, except we're not just calculating some integrals. We're trying to approximate a target function, f star. So we want to have some approximation results like this. This will be the analog of that. And then this guy will be the analog of the variance. And here the variance depends on the particular approximation scheme, Monte Carlo scheme. So this is a really trivial scheme, but if you have, in practice, usually we have some improved version of Monte Carlo, and then the variance would be defined differently. And here too, that this depends on the particular machine learning model. So we want to pick machine learning models for which this quantity is small. Well, first of all, we need to ask what this quantity is. What is this quantity? How, given a machine learning model, is this true? And if it's true, how do we define this quantity associated with that particular machine learning model? And then we try to look for machine learning models for which this quantity is small. Okay, now how could this be true? How could this be true? Let me give you some intuition. And that has to do with how we can represent a function. So this is a classical Fourier transform, representing a function through its Fourier transform. So A will be f hat, the Fourier transform of f. And associated with this representation, we have this usual discretization on a uniform grid, FFT approximation. And this is FFT approximation. The error in this approximation suffers from the curse of dimensionality. So this is well known. This is why FFT doesn't work in high dimension. Suppose our function admits this representation. The only difference between the Fourier representation and this representation is that d omega is replaced by pi of d omega, where pi is a probability distribution. So this d omega cannot be normalized. So in this representation, the function becomes an expectation. So we can do Monte Carlo. So, and then in Monte Carlo approximation, the error does not suffer from the curse of dimensionality. So that's one thing. The second thing is that this guy, this approximation is nothing but a 2-layer neural network. So as a matter of fact, we can write this as AJ, and then define this function sigma, like so, and then this expression becomes this expression. And this expression is nothing but a two-layer neural network. Yeah, this is exactly the definition of two-layer neural network, by the way. Two layers because we have two sets of coefficients. So what I'm saying here is that as long as a function admits this kind of representation, then with some finite moments and stuff like that, then that function can be approximated by a two-layer neural network without a curse of dimensionality. So this is a very important intuition, I would say. So now let's go back and look at two-layer neural networks. As I said, this is the definition of two-layer neural networks. Now sigma is the general activation function. As a matter of fact, it's not general. This sigma should be the ReLU activation function. So sigma x equal to x if x is a positive, and it's equal to 0 if x is negative. So sigma is that specific function. And this is the so-called hypothesis space for two-layer neural networks. And we want to ask the question, what kinds of functions can be approximated by these two-layer neural networks efficiently? Efficiently, by which we mean that the convergence rate does not suffer from the curse of dimensionality. So we want to define the class of functions that's naturally associated with this particular machine learning scheme, namely two-layer neural network model. In order to do that, so that would be like the replacement of Sobolev spaces. So Sobolev and Bessel spaces, these guys don't work in high dimension because they're still too big. As a matter of fact, in high dimension, if we talk about C5 or C500, really doesn't make much of a difference. As a matter of fact, I would even claim that finite difference and differential equations don't make much of a difference. In low dimension, it makes a huge amount of difference, whether it's a difference equation or differential equation. In high dimension, I would say that's not so important. What's important is it's a different. We need a different way to quantify the complexity of functions. Sobolev spaces is not good enough. It's not going to be useful. Okay, so how do we do that? Well, for this particular machine learning scheme, in order to define the class of functions, we do the following thing. So let's first consider functions that emit this kind of a representation, where rho is a probability distribution over the parameters a and w. And you can see this is nothing but a continuous form of this guy. So for functions that emit this representation, we define a norm. Well, never mind whether it's really a norm or not. Okay, let's just call that a norm and use that terminology in a loose fashion. So that's just the mixed moments, some mixed moments. And we need to take infimum over all possible rows because the rows for a given f, the rows for which such that this holds is not unique. So we take an infimum over all such rows. Okay, and we define this quantity to be the norm associated with f and call that Barron norm. And we call this Barron norm because Barron, Andrew Barron, spent work done on approximation theory for two-layer neural networks for a very long time, starting with this very classical paper. And then for a continuous function whose Barron norm is finite, we call that Barron space. Barron space is a space of functions for which Barron norm is finite. One can actually show that if you replace 2 by any p, so for example, this will be, you could think this is the L2 version. You can ask, what about LP version, p from 1 to infinity? One can actually show that all these spaces are equivalent. So it's not like the usual LP. So all these spaces are equivalent. You can replace 2 by 1 or 2 by infinity. It doesn't matter. So anyway, so this is we claim. I'm going to claim that this is the right space. So before I tell you why I make that claim, an obvious question is what kinds of functions admits this representation? What kind of functions are Barron functions? What kind of functions are Barron functions? And this is not an easy question to address. So there are some results due to Klossowski Baron, and also if you take a look at this paper, there are some sort of structural theorems about Baron functions. But I would say this is a subject that requires much more effort. Well, the reason I claim that this is the right function space is because direct and inverse approximation theorems are valid in these spaces. For example, one can show, so this is actually, it's also a theorem in quotation marks because, well, actually, this is a rigorous theorem. This is a rigorous statement. So one can show that if a function, for any function f whose Baron norm is finite, there exists a two-layer neural network for which this is true. And conversely, given any function that can be approximated by two-layer neural networks with some uniform bounds, then the target function has to be in Baron space and the Baron norm has to be finite. So these are very easy theorems to prove. This is just some compactness statements. Now, that's one part of the error that we need to think about. The other part of the error we need to think about is the fact that is associated with the fact that we only have a finite data set. So what could happen is that on the data set, you have very nice approximation, very accurate approximation, but away from the data set, your model, machine learning model, could be very far away from the target function. So this can happen. This is even in a very classical sense. This is the so-called wrong phenomena of polynomial interpolation on uniform grids. You can see that we had, the target function is very, very nice, but your interpolant is very far from the target function, away from these training data set. So we don't want this to happen. This will be bad. In other words, we don't want the so-called training error and testing error to be very different. So when we do the training, we minimize this thing because we are given data on these data sets. So we can only work with this. But in reality, we're really interested in minimizing this because that's we're not just interested in the training data set. We're interested in the samples according to the probability distribution mu. So we're really interested in this thing. So one needs to be not too far apart. Now, on the first, if you look at this the first time, you might think, well, this is just the Monte Carlo discretization of this. They should not be very different. The difference should be like 1 over n, 1 over square root of n. Right? As I said earlier, well, that argument is not true because the value of theta is the optimal parameters that we obtain through the training process. And that training process produces a lot of correlation between theta and all these xj's. So my previous argument requires these xj's to be IID, everything to be IID. Now it's not the case because this theta, the trained parameter is very highly correlated with these guys. So these can be very different. These quantities can be very different. So how do we estimate the discrepancy between these two quantities? Well, we don't have a very good idea. In the absence of a good idea, let's just try to bound this difference by the supremum. And again, this is difficult to control, but turns out this is the equivalent to something else called a Rademacher complexity of the hypothesis space against a particular training data set. And the Rademacher complexity is defined as follows. It roughly measures, given a set of functions H, Rademacher complexity roughly measures how that set of trial functions can fit random noise. So Ci is a set of IID random variables that takes the values plus minus 1. And we just try to pick a function and fit Ci and see how well we can do that. And that quantifies the Rademacher complexity. For example, you can show that if you take a unit ball in continuous space, if this H is a unit ball in the space of continuous functions, then this we can choose H so that this is equal to 1. So then, therefore, this would be equal to n. So this will be order 1. So the Rademacher complexity will be the 1, order 1. This is the worst case scenario. If you choose H to be unit ball in the Lipschitz space, it's not quite as bad, but then this quantity B would be like 1 over n to the 1 over d. So I didn't write this, but that's an interesting exercise. So because that's very much related to Wasserstein metric. Anyway, so unit ball in unit ball Rademacher complexity is also large. But it just so happens that for the unit ball invariant space that we just defined, the Rademacher complexity scales like 1 over square root of n. So 1 over square root of n is the best scaling one can hope for, roughly speaking. And one can show that indeed for the unit ball in invariant space, that's the case. So with these kinds of results, so estimation error and approximation error, with these results in place, one can now consider a regularized machine learning model. So this is the usual empirical risk. It's just this guy. And then if we regularize by the barren norm, so this quantity here is really just a barren norm. We regularize by the barren norm, and this scaling, these kinds of scaling are also standard in machine learning. Now, if we consider this regularized model, then one can show that every minimizer of that regularized model satisfies this kind of error estimates. So this is a typical theorem in machine learning. It looks as follows. Assume that the target function is invariant space. Then for any delta, small number delta positive, with probability 1 minus delta over the choice of the training data set, one has the following estimates. And these are logarithmic terms, which are not important. These two terms are the important ones. This is the approximation error. This is the estimation error. So the approximation error scales like 1 over m. It's not 1 over square root of m, it's 1 over m because this quantity itself is squared. These guys are squared. So we have 1 over m, not 1 over square root of m. But here we have 1 over square root of n, because here we're looking almost like the Monte Carlo approximation error. And the coefficients are the barren norms. So this result shows that, well, in the hypothesis space of two-layer neural networks, as long as the target function is barren space, one can approximate that function very well with a Monte Carlo kind of a convergence rates by two-layer neural networks. Now, similar results can be proved for the random feature model. This is a linear model, and the corresponding function space is the classical reproducing kernel Hilbert space. For residual networks, so this is a very popular neural network model. I don't have time to explain that thing, so I'm going to skip the details. But there's also, one can define the analogous barren space, analogous function space for ResNets, and this is what we call flow-induced space. And for multilayer neural networks, one can also define an analogous function space. That's what we call multilayer spaces. It's not. Anyway, now these spaces with these kinds of okay, if the target function belongs to these spaces, then one can prove approximation results like that, generalization error results like that, namely after some with some regularization, then the global minimizer satisfies these kinds of estimates, where this is the approximation error, this is the estimation error. So as I said before, these guys are like the variance in the Monte Carlo algorithm, and we want to do variance reduction. So now you might want to ask, well, what is the variance reduction here? It turned out one can show that as the number of layers increases, these norms decreases. So in a way, that's variance reduction. In particular, ResNet is the best because it's got the smallest norm and got the biggest function space and the smallest norm. I need to speed up a little bit because I want to finish with one more topic, which is how do we formulate machine learning model from a continuous viewpoint. As a PDE person, I want to see every problem as a continuous problem, either calculus variation problem or PDE problem. So how do we do that? Well, it actually, if you, as a calculus variation problem, we just want to minimize this. Now, here, of course, the key thing is how is this function represented as how this function depends on the parameter theta. So theta denotes some abstract parameter. So how do we select a particular representation of the function in terms of a parameter theta? That's the key issue. For example, well, before we consider this kind of representation, well, actually, before we consider this kind of representation, when we define Barron space, this was the representation that we considered. Well, since A is linear, we can take the expectation, take the marginal of rho with respect to A, and then the marginal would be probability distribution on W, and that's pi. So then this representation can be written as this. So these are equivalent. Or we can consider something more general. Namely, we can replace this part by a more general function phi. And this is called feature function. In the machine learning, this is called feature function, and U is called a feature vector. So this is the one kind of ways to represent functions, and we call this integral transform based representation. Another way one can imagine is the following. Well, all we have to do is to produce some nonlinear functions, and we use them as the trial function to fit the target function. And one way to do that is look at the flow map. If we look at any kind of ODE and look at the flow map, and then do some contraction, then we produce functions. Of course, the question is, what does the right-hand side look like in the ODE that defines the flow map? Well, we can use these ideas, stick them into here, and consider these kinds of ODEs, and look at the flow map, and then take the contraction, and then produce the nonlinear functions. Here, we can regard rho as being a parameter. Here, in this representation, we can regard A as the parameter, with pi being fixed. Or we can regard both as being the parameter. And here, in this representation, we would have the one parameter family of probability distributions as being the parameter. So in any way, so these are representations of functions, possible representations of functions in terms of some form of expectation. So what's important is that it's either directly represented as some expectation, or indirectly through this ODE represented indirectly as some form of expectation. And represented is this expectation structure is important because we're dealing with high dimensions. Okay, so that's the basic idea. So now with these kind of representations, we want to minimize the free energy. In order to minimize the free energy, we want to define some gradient flow. In order to define the gradient flow, we need to distinguish the kinds of parameters we have. For example, in this representation, A and W are very different kind of parameters. W is a probability distribution. So when we define the gradient flow, we need to make sure that gradient flow produces probability distributions. So we do it this way. We first define some chemical potential. This is just the usual variation of gradient. And then we use some fixed law to define the velocity field, and then the current and the continuity equation. So this is a gradient flow for pi. And one can show that as long as the solutions are smooth, the pi will remain to be a probability distribution. And incidentally, this is also the gradient flow of R in the with respect to the Wasserstein matrix. For A, it's a so-called non-conserved order parameter. So we don't have to do this. We don't have to take to be this complicated. We just take the gradient, usual gradient descent. By the way, this would be like the Allen-Kahn. This would be like the Kahn-Hilliard equation. So now, once we have these like PDEs, we need to solve the PDEs. We need to discretize these PDEs. Well, the first thing to do is to discretize this functional, and that we can do very easily by just using the data. So then this becomes the empirical risk, not the population risk. And the next thing is to discretize these PDE-looking equations. Now, in this case, the method of choice is the particle method, because we're thinking about high dimension. So we need to do particle method, which is the dynamic version of Monte Carlo. If you think about filtering, now filtering is usually a high dimensional problem, and we've all heard about particle filtering. We never hear about finite element filtering or spectral method filtering because they don't work in high dimensions. But if you really want to use these kind of ideas to solve a low-dimensional PDE, like a Navier-Stokes equation, then you don't have to do particle method. You can do spectral method, and then this would also work. Although nobody has really tried it out. So how do we? Let me give an example of the discretized scheme. So let's think about this representation, and then the gradient flow looks like this. Is defined as follows. We discretize by particle method, which means we replace this probability distribution by empirical probability distribution centered on these particles, so-called particles. So denote uj to be these particles. And then one can actually prove, well, it's a simple observation that these two problems are equivalent. So namely, if we define, given a set of particles, we can, namely a particular realization of these coefficients, we can define a two-layer neural network. Then we can define the population risk associated with that two-layer neural network, and that's a function of these position of the particles. One can show that this PDE, continuous looking PDE, is actually equivalent to this ODE, gradient descent ODE. Well, it's more or less obvious, which means that if we take a set of particles that evolves according to that PDE, then this is actually the exact solution. If we take a set of particles that evolves according to this set of ODE, then this is exactly the exact solution of this PDE. So what I've done here is that starting from this continuous formulation, I've really derived this gradient descent algorithm, which is nothing but the gradient descent algorithm for two-layer neural networks, except this two-layer neural network is scaled, has this 1/m scaling. Now let me make a remark that you probably have heard this work about mean field approximation, a mean field approach of analyzing two-layer neural networks. So the idea is that by looking at two-layer neural, they're interested in studying the continuum limit of two-layer neural networks and view the neurons as interacting particles. And then the setup is very naturally in the mean field regime because the particles interact with each other through the functions that they construct. They don't interact with each other directly. So this is the mean field regime, and the solution, the limit equation, is exactly this equation. So here I'm taking the opposite approach. I started with a continuous framework, continuous formulation, and then discretize the continuous formulation, and then recover these two-layer neural network models. Now, this approach, in my opinion, is probably, in my opinion, is more intrinsic, and it actually is more general. I don't have time to go through this, but it's actually more general. Now, let me take a comparison between this is scaling and this scaling. This is the usual scaling that people use in practice. And this is the scaling that we were considering from a continuous approximation or mean field approximation. Because the only difference is that we have a 1/n coefficient here. But the gradient descent dynamics behaves very differently. This little factor actually changes a lot the gradient descent dynamics. In particular, you can see that the following pictures. If you look at the test error in the MN plane, so M is the number of neurons, N is the number of training, is the training data size. You can see that there is a phase transition between a nice phase where the test error is small and a bad phase where the test error is big. Imagine your parameters, you choose your network structure that falls in here. Then you will be in bad luck because the performance will be bad. Now, this is two-layer neural networks. There are evidence, not very conclusive, but there are evidence that the phase diagram for multi-layer neural networks is even more complicated. And I think I hope that's one way to explain why tuning parameters is hard for multi-layer neural networks, because the good phase in the phase space, on a phase diagram is really small, and you need really to tune your parameters in order to fall into the good phase, the nice phase. In contrast, if we did this scaling, then the errors behave very smoothly, and you don't have to work very hard to tune the parameters. Let me finish by looking at the ODE form. So I said that you can also represent functions this way by looking at the ODEs and then do a contraction to produce the function. And our objective is to minimize this test error. Here, this is the control problem with rho, tau, well, one parameter family of probability distribution as being the control. So as a control problem, we can write down the maximum principle. And this is maximum, and to do that, we define Hamiltonian on the state space, on the state, co-state, and control. Now the control is a probability distribution with finite second moment. And then this is our Hamiltonian. Maximum principle says that for each tau, pseudo time tau, the optimal control actually maximizes the expected Hamiltonian. And the states and co-states evolves according to this forward and backward equation. So this is exactly convergent maximum principle. And you can also ask, how do we define the gradient flow? In order to define the gradient flow, like we did before, right? So in order to define gradient flow, in this case, we just have to replace this equation by the gradient flow equation. And we can also show this is some sort of Wasserstein metric, Wasserstein gradient flow. So this will be the gradient flow for this flow-based model. You can see this is actually one parameter family of gradient flows, one for each tau. And then if you discretize this guy according to the simplest ideas, namely forward Euler and backward Euler and stuff like that, you can see that you actually reproduce the gradient descent algorithm for ResNets, including the forward and backward propagation. So what I'm saying here is actually the ResNet algorithm can be recovered through discretization, particle method discretization. But we don't have to do the gradient flow. We can actually try to formulate algorithms directly from this maximum principle. And that can also be done. It can also be done. So this is just discretization of that maximum principle. And the result, since I'm running out of time, yeah. Oh, I'm really running out of time. And the result's not so bad compared with stochastic gradient descent algorithms. So these are two different sets of tests. This is the one, a nice initial condition. This is a bad initial condition, meaning that the variance is big. You can see that it converges much faster. The maximum principle based on algorithms converges much faster than the stochastic gradient descent. Okay, so actually this is what I want to say. I think if you want to ask the question, what do we really learn from machine learning? What's really new in machine learning? I think it's actually this way of representing functions. You try to think of ways of representing functions as expectations. This way, or actually this way. I didn't explain this. This corresponds to multi-layer neural networks. But think about how to represent functions as expectations. And then any particular representation, it would give rise to a continuous machine learning model, which upon discretization using particle method, spectral method, or any other numerical method would give rise to specific algorithms. Summarize, I talked about numerical analysis, viewpoint to machine learning, and if you're interested in looking at more details, there are these review articles in my webpage. I'm sorry for running out of time. I usually don't, but today I ran out of time. Thank you very much for your attention.
It's perfectly okay, Weinan. Thank you very much for your very interesting talk. Thank you very much and congratulations.
You're welcome.
Let us go to questions. I can see already that Albert has raised the hand. Please, Albert.
Thank you very much for a nice lecture. So I have a sort of general question. So in the usual low dimensional paradigm of solving PDEs by finite elements, so you recall the classical approximation result involving Sobolev space, and they usually come together with results on PDEs, elliptic or parabolic PDE, that says that the solution indeed live in this Sobolev space. So everything sort of matches very nicely. And now you switch to this high dimensional paradigm and you focus your attention, you decide you center to the example of this Baron class, which, by the way, I think it's a quite restrictive class, because I think asking L1, in fact, you ask for a sort of integrability condition on the Fourier transform in high dimension, which is in a way asking quite a lot of smoothness, because to be integrable in high dimension, you have to decay quite a bit. But okay, but my question is more, you gave a lot of example of high dimensional PDEs. Black-Scholes, molecular dynamic, all kind of, do you have evidence or theorems maybe that the solution to these models will belong to the Baron class in order to
yeah, okay. So this is a very, very good question. And obviously it's not very much work done, but there are two papers that's written on this topic. Where Stefan Wojtowski and I wrote a paper, which, well, very simple paper, but we just write down solution formulas and check whether it's in Baron space. For example, the Hamilton-Jacobi-Bellman equation, one can show that if the initial data is in Baron space, then the solution is in three-layer space. So we cannot show that the solution is a Baron space, but we can show the solution is in the three-layer space. The extension of Baron space for three-layer neural networks. So there are some results of that type. But let me emphasize that the way I defined Baron norm here is not the same as the way that Baron defined the Baron norm. Baron defined the norm using Fourier. This is not the Fourier. So there's actually a difference between these two spaces. I think it's perhaps a bad idea to call this Baron norm because it got confused with the norm that Baron defined. So we now call Baron's norm Baron spectral norm. Well, but please note that this is not the same as the Baron norm, as a norm that Baron defined using Fourier transforms, which may still be very restrictive, but I just want to make that point because it's caused a lot of confusion.
You use
yeah, but for the regularity theory of PDEs, yes, this is a very good point, and there are some very elementary work in this direction. But for example, for nonlinear PDEs, for this nonlinear PDEs that I talked about earlier, I'm pretty confident that one can show similar results, namely that the solution belongs to multi-layer spaces. It's not clear that one can show that the solution belongs to Baron space because Baron space is a two-layer neural network. But you can show that the solution belongs to multi-layer spaces with 3 layers, 4 layers.
Thank you.
Thank you, Albert. Other questions? I have a question, Weinan. You mentioned quite quickly that once you have applied the Pontryagin maximum principle, numerically you can implement, for instance, what you've called the MSA method of successive approximations, which is actually historically the very first method in optimal control. In some sense, the coarsest one, but which is perfectly adapted to the set of to this context, because we are in a high dimension. Anyway, here, so I understand it can be applied, of course, in the continuous setting, but you also apply it to the discretized setting, right? And so my question is on the fact that between continuous and discretized setting, there is a discrepancy of Pontryagin maximum principles, in the sense that the maximization condition of the Pontryagin maximum principle is not always valid in the discretized setting. So how do you deal with this issue?
Okay, if you started out with the discrete neural network model, then you're right. I mean, it's not clear that the Pontryagin maximum principle is true. But if you started out with a continuous continuous formulation, so I started out with a continuous formulation, then the maximum principle is true. I just discretize then in this case there is a maximum principle. I just discretize this guy.
Yeah. This is why you advise to start from the continuous version.
Right.
Which is more well posed in some sense.
Yeah. I feel there's a lot of room in this thing here that's not explored.
Yeah. Okay. And apart from MSA method, have you some advice for other numerical approaches to implement the solution, the solving of this optimal control problem?
Well, there are two extremes. One is the maximum principle, one is the gradient descent, right? So this is how almost everybody in machine learning does this. And I was just discussing this. Certainly there could be a lot of hybrid between the two. Perhaps best is the hybrid. Because this is the one extreme, this is the other extreme. This is the extreme, one maximizes the row each step. There are two expensive operations going on. One is backward-forward propagation, and one is maximization. So here, for each backward-forward propagation, you maximize, to convergence. So that's overdoing the maximization. Here, for each backward-forward propagation, you just do one step of SGD, and that's really wasteful. So these are both extreme cases. So I think there's a lot of room in between.
Thank you, Weinan. Are there some other questions or comments in the audience?
Emmanuel, here's Olga. I cannot raise my hand. Thank you, Weinan, for the very nice talk. I had also a question regarding this part on this algorithm. And this is that when you take this path on this optimal control viewpoint, then the analogy with the neural networks, it is very clear, but at every layer, in fact, you need to keep the dimensions fixed, right? As far as I understand. And my question is whether you think that this approach can be somehow competitive with the more classical point of view due to this restriction, and also to the fact that in the terminal function, you also don't have a lot of room to optimize over.
Yeah, that's a very good point. So I can add a matrix here. I can add a vector here. So that sort of helps things. But in between, it's true. In this kind of a situation, in between, the dimensionality is fixed. So,
do you have any idea whether this has a lot of impact, or how to add this kind of flexibility?
I don't know how to add flexibility in between, but if you are okay, it really depends on what you do in practice, right? And if you want to construct 3 layers or 4-layer neural network, you don't think about this. This would be wasteful. You think about this. So this is a this sort of stuff, which would be it's like an extension of this guy. This is a 2-layer neural network. You can extend this to 3 layers, 4 layers. So you think this way. This way is really like a resonance where you want to have lots of layers, thousands of layers. Then you think this way. Then perhaps you don't want to change the dimensionality in between too much. These are 2 different extremes.
Regarding the fact that we can interpret the backpropagation as the integration of the adjoint variable. So yes. Do you think that this could be somehow of value to the machine learning community to understand that there are sometimes numerical stability issues that arise in the classical backpropagation that could be maybe better understood through the fact that we are optimizing via an adjoint variable, and which we could somehow have more flexibility to add an integration scheme over that variable. Can this be somehow of value for this machine learning community, and how to bring this to them in a more practical way?
I think that's a very good idea. It's a very good suggestion to try to understand the instabilities in backpropagation through the adjoint equation. Yes.
Thank you.
I hope you'll work on it. There's lots of good problems here. Yeah, I think that would be worthwhile.
Okay, thank you again. Any further questions or comments? No other question? Okay, so in that case, let us thank Weinan again for his very nice talk.
Thank you very much.
Thank you very much, Weinan. Thank you for your talk.